We just finished working on solving problems and determining the pH of strong acid solutions. Now we're going to work on determining the pH of weak acid solutions. A much more pertinent problem to our lives, because weak acids are much more dominant in our environment and in our daily lives than strong acids are. So how do we recognize the difference between the two in the first place? A strong acid, well, what were they? Remember, we got 3 from the periodic table: hydrochloric, hydrobromic, and hydroiodic. And then we had to know the names and formulas of the other 3: nitric, sulfuric, and perchloric. So those were our 6 strong acids. How do we recognize a solution of a weak acid? It's just not one of the 6. That's how we're going to do it. So know those names and formulas of the strong acids, and then it'll be really easy to recognize a weak acid. For any weak acid, how can we write its acid ionization or dissociation reaction? And this is the general chemical formula, HA. So you write the weak acid dissociates to hydrogen ion and its conjugate base. And notice how the backwards arrow is huge. These equilibria all lie dominated in this form. They hardly dissociate at all. That's why they're weak. And we should also have AQ on everything, but I'm pretty sure we won't be doing that for long, because everything always has AQ on it. All of our reactions I have AQ. These are all aqueous equilibria that we're talking about. Weak acids dissolved in water. How should we write the equilibrium constant? We're going to call them acid ionization constants and give them the symbol Ka. How do you write that expression? Well, Ka, as all equilibrium constants, products over reactants. Leave out pure liquids and solids. So it's just products over reactants. How about this? Here's a table of a lot of acid ionization constants. And here's the names and the formulas, and there's our Ka numbers. Okay, let's play around with this a little bit. Larger, smaller, or is there no effect? Acid ionization constant means it is a stronger acid. So the bigger or smaller Ka is it a stronger acid? Well, if this is a bigger number, that means we have to have more on top here, right? So that would mean that we have more dissociation. So larger acid ionization constants means it's a stronger acid because of a higher degree of dissociation. Table 16.1 lists the acid ionization constants for some weak acids. Which acid listed is the strongest? Okay, so do you see the largest Ka in here? I see a 10 to the negative 2. Can't get much larger than that in this table. Here's another 10 to the negative 2. There's another 10 to the negative 2. But which one's the biggest? 5.6 is bigger than 4.8 or 1.1. So oxalic acid is the strongest. The weakest, I think it's going to be hard to beat that 10 to the negative 13. Oh, here's another 10 to the negative 13. And it's a little bit smaller, 1.2. So hydrogen sulfide. Write the dissociation reaction and Ka expression for the strongest acid in the table. So a little practice on that. This was our strongest weak acid. You always write the conjugate acid, dissociates to hydrogen ion, and the conjugate base. And the Ka expression. Products over reactants. Hydrogen ion conjugate base all over the conjugate acid, the weak acid. For any aqueous weak acid, HA, solution, what two concentrations are always roughly the same? Can you tell? We're going to have a bottle of this stuff, and we put it in water. It almost all stays in this form, except maybe 1 out of every 10,000 molecules dissociates. But when one does dissociate, dissociates into hydrogen ion and the conjugate base. 1 to 1. These two are going to have the exact same concentration. So the hydrogen ion equals the conjugate base concentration for pretty much every single one of these problems. Let's practice calculating the pH and equilibrium concentrations of some weak acid solutions. Formic acid is used to make ethyl formate, an artificial rum sweetener. What is the pH of a 0.1 molar solution of formic acid? Okay, so they told us the concentration of this acid, and they want to know what pH is. Now remember, pH is just the negative log of the hydrogen ion concentration. And before, didn't we just put that number right in there? But that's for strong acids only, so we can't do that. We have to find the hydrogen ion concentration, because for weak acids, like I said, only 1 out of every 10,000 or less of these weak acid molecules actually dissociates. So we have to calculate. That's an equilibrium concentration. It's an equilibrium composition problem. So that means we have to do ice. Okay, so do ice, we need a reaction, and the reaction we're going to use is the Ka reaction. So let's write the Ka reaction and make an ice table. So the Ka reaction is always the conjugate acid dissociates to hydrogen ion and the conjugate base. And let's make our ice table then. The initial row, formic acid, we have 0.1 molar initially. We don't have any hydrogen ion or formate. Change row, negative X for reactants, positive X for products. So 0.1 minus X. Add up our change in initial row, X and X. So the hydrogen ion concentration is going to be X. Notice our formate is also X. They're the same concentration, but X is what we're after. How are we going to find it? Substitute into the Ka expression. Substitute into the Ka expression. So let's see what that's going to look like. Okay. Ka is equal to products over reactants. Hydrogen ion, conjugate base, concentration, all over the concentration of the weak acid, HCHO2. So let's substitute those numbers in. Our Ka from the table is 1.7 times 10 to the negative 4. Our hydrogen ion concentration is X. Our formate is X. And our formic acid is 0.1 minus X. Okay, now this is really looking ugly. This looks like a quadratic formula problem, but it's not. And you're going to like these. Why? Because Ka is really small. And the smaller the better. When Ka is 10 to the negative 4 or smaller, we can do this. What am I talking about here? If Ka is really small, that means that I don't have much product at all. This hardly happens. The reaction is all going backwards, right? We hardly get any product at all. In fact, we get so little that x is going to be extremely small. So x is in a very, very small number. 0. I don't know, 6 zeros and a 1 or something. X is going to be really small. So if you take 0.1 minus a really small number, you get 0.1 again. So this is approximately x times x all over 0.1. Because 0.1 minus a very, very small number is 0.1. We drop the minus x. So now it's pretty easy to solve. We'll bring 0.1 to the top, take the square root. So it's going to look like this. 1.7 times 10 to the negative 4 equals x squared all over 0.1. Right? So bring the 0.1 to the top, take the square root, and we'll have our x. So 1.7 times 10 to the negative 4 times 0.1, it equals, take the square root, and you get 4.12 times 10 to the negative 3. Okay? So 4.12 times 10 to the negative 3. And we wanted to know pH. pH is the negative log of the hydrogen ion concentration. Well, that's going to be the negative log of x, because that's what x is, right? X is our hydrogen ion concentration. So take the log of it, negative 2.4. Well, 2.38 or so. Okay? Let's try this again. Find the pH of a 0.38 molar hydrogen cyanide solution. Ka is 4.9 times 10 to the negative 10. So write the Ka reaction, do ice, see if you can get the hydrogen ion concentration. So there's my Ka reaction. Make an ice table. I have 0.38 and nothing else present. Minus x, x and x, 0.38 minus x for an equilibrium concentration for hydrogen cyanide, and x's for hydrogen ion and cyanide. Now we substitute into our Ka expression. Hydrogen ion, cyanide over hydrogen cyanide. What do I get? I get 4.9 times 10 to the negative 10 has to equal x squared divided by 0.38 minus x. I have 10 to the negative 10, so that definitely, that's definitely smaller than 10 to the negative 4, so I can drop that minus x. So this is approximately x squared all over 0.38. So my equation looks like this. 4.9 times 10 to the negative 10 equals x squared all over 0.38. So bring 0.38 to the top, take the square root. 4.9 times 10 to the 10 negative times 0.38 equals, take the square root, about 1.36 times 10 negative 5. And my hydrogen ion concentration is x, so pH would be the negative log of 1.36 times 10 to the negative 5. That's my hydrogen ion concentration. About 4.89. Find the Ka for a weak acid, HA, if the pH is 2.8 and and the concentration of HA is 0.52 molar. Find Ka. So, well, let's just start with that then. Ka is equal to what? Well, Ka is products over reactants. If you forgot how to write it, just write the Ka reaction. Ha goes to H plus and the conjugate base. So Ka has to be the concentration of hydrogen ion, concentration of the conjugate base, all over Ha. Okay. So how are we going to get this? Well, they told us what Ha is, right? Well, that part's done. They told us that one. We got that. Did they tell us anything else? They said the pH is 2.8. We can get what from that? The hydrogen ion concentration. Okay, so we're only missing one thing, A minus, and we'll be done. Do you remember the trick? What two things were the same? They break up, they dissociate 1 to 1. For every hydrogen ion, you get one conjugate base molecule. So they are exactly the same. If you know pH, that number you're going to substitute in both places. Okay, let's try it. So the pH, do you remember doing this? pH is negative log of hydrogen ion concentration. Raise both sides to the 10 power, bring that negative sign over. 10 to the negative pH was our hydrogen ion concentration. Remember doing that? So our hydrogen ion concentration is 10 to the negative 2.8. What is that? 2.8 negative, shift 10 to that power, 1.58 times 10 to the negative 3. So that is my hydrogen ion concentration. That is also concentration of A minus. Right? They break up 1 to 1. For every one hydrogen ion, you get one conjugate base. So we're pretty much done. Just substitute everything in and plug and chug. So Ka is going to be hydrogen ion, which we said is 1.58 times 10 to the negative 3. A minus is 1.58 times 10 to the negative 3. Concentration of HA was 0.52. So what do we get? Squared divided by 0.52, about 4.83 times 10 to the negative 6. That's my Ka. Find the concentrations of hydrofluoric, hydrogen ion, and fluoride anion in a 0.15 molar solution of HF, and they give us the Ka. So again, this is an ice problem of the Ka reaction. So let's write that Ka reaction. Do ice, 0.15 initial, nothing for the others, minus x and plus x. 0.15 minus x is an equilibrium concentration for hydrofluoric, and x is for hydrogen ion and fluoride anion. Okay. Substitute into our Ka expression. Hydrogen ion, fluoride, over hydrogen fluoride. Okay. Ka is 6.8 times 10 to the negative 4. So 6.8 times 10 to the negative 4 has to equal x times x divided by 0.15 minus x. Well, remember, thank goodness, 10 to the negative 4, so we can drop the negative x. Good deal. So 6.8 times 10 negative 4 is approximately x squared over 0.15. What's my x then? 6.8 times 10 to the negative 4 times 0.15 square root. You get about 0.01. So they want to know all these concentrations now. Concentration of hydrogen ion is X. And so is F minus. And X is 0.01. So the concentration of fluoride is X, which is 0.01. Concentration of HF, again, from our equilibrium row, this is where all of our answers are. It's 0.15 minus X, which is 0.14. There's all of our answers. If the pH of an unknown HNO2 solution is 1.93, what is the unknown concentration of the HNO2 solution? Sound familiar? They tell us pH. We'll use that to get the hydrogen ion concentration and the NO2 concentration. Okay? So then we'll know both of those. So since this is not an ice problem, when they give you the pH, you know the equilibrium composition. So you just go ahead and start working on this. What expression do we need to write to find this concentration? The Ka expression. Here's our Ka reaction. So we can write the Ka expression. Ka, hydrogen ion, conjugate base, all over conjugate acid. Okay, so it looks to me like we'll know these two, and we even know Ka. They told us that. So this is what we'll solve for. That's our big game plan. Okay. So let's get that hydrogen ion and conjugate base concentration. The hydrogen ion concentration is 10 to the negative pH. It's going to be 10 to the negative 1.93. So my hydrogen ion concentration is going to be 1.93, make it negative, shift 10 to that power, about 0.0117. So that means my conjugate base must be 0.0117 Okay, so we just plug all that stuff in, and we'll have our answer. What did we say the Ka was? We said it was 4.5 times 10 to the negative 4. So 4.5 times 10 to the negative 4 has to equal hydrogen ion times NO2 minus, but we said they're both 0.0117. So I'm just going to square it, divided by what I'm looking for, my unknown concentration of the conjugate acid. So how are you going to solve for it? Remember the diagonal. Just switch those two, and you'll have it. The concentration of HNO2 is going to be 0.0117 squared divided by 4.5 times 10 to the negative 4. Squared divided by 4.5 times 10 to the 4 negative, about 0.31. Okay. So these problems really are not so bad in determining pH and finding the equilibrium concentrations of the components of a weak acid solution, as long as your Ka is 10 to the negative 4 or smaller. These problems aren't bad at all. So I guess you just don't want to see a problem that involves 10 to the negative 2 or 10 to the negative 3. Those acids, you're going to have to do a full quadratic equation on those.